This lecture will discuss vapor compression refrigeration systems. So far, we've only looked at refrigeration systems from this high-level energy transfer point of view. So let's just review this before we go into the details. So we have here a cold temperature reservoir and a high temperature reservoir, and we have between those reservoirs some machine that is operating in a cycle. It's drawing energy by heat transfer from the cold reservoir. It requires work in order to do that, work from the surroundings, and it delivers energy by heat transfer to the high temperature reservoir. So what we're going to look at now is what is happening inside of this cycle. Now, a couple of other things that we should review before we look at those details. This is the definition of the coefficient of performance for a refrigerator. So the thing that we want the refrigerator to do for us is extract this energy by heat transfer from a cool space. So that goes in the numerator, QC. The thing we need to pay for to make that happen is the work of the cycle. So the magnitude of that goes in the denominator. So that's the coefficient of performance for a refrigerator. For a heat pump, there's a similar expression, but the numerator is QH. Now realize that that is valid for any refrigerant. It doesn't matter how good it is at doing its job. That's the definition of the coefficient of performance. The maximum possible value that this can attain, however, is a function only of the two temperatures that it's working between. So that's Tc over Th minus Tc. So this can never get any bigger than this value here. Now what we're going to do is go inside this cycle and see what components we need to hook together to make a vapor compression refrigeration system that has this overall effect. Well, we're going to begin with a cycle that we've already seen. We've talked about a Carnot cycle. Only now what we're going to do is operate that Carnot cycle in reverse. So these are the same four processes that we talked about when we introduced a Carnot cycle as a heat engine or as a power cycle. The difference is there we started off with this process and they happened in that order. Whereas now we're going to start off with this process and they'll happen in this order. So they're just happening in the opposite order. So the first is a reversible adiabatic compression, followed by a constant temperature heat rejection, then reversible adiabatic expansion, and finally constant temperature heat addition. Now remember, because this is a Carnot cycle, all of these processes are reversible. In addition to looking at a Carnot cycle, we're going to be looking at a working fluid where we're in or near the liquid vapor region. So we're going to soon take our Carnot cycle and put it on this set of TS coordinates, and notice that I have a saturated liquid and saturated vapor lines already drawn on here. So we're going to be operating a Carnot cycle in the liquid vapor region. Now, the two temperatures that we're operating between are TH and TC, and because this axis is temperature, those constant temperature processes are just going to be horizontal lines, and because the other two processes are reversible and adiabatic, they'll be vertical lines. And you'll remember this when we introduced TS diagram before, that a Carnot cycle is just a rectangle on TS coordinates. Well, one of the reasons that we like to use substances that are changing phase in equipment like this is that we can achieve a constant temperature heat transfer process that is also constant pressure. Because we remember that if we're inside this liquid vapor region, a constant temperature line and a constant pressure line coincide. So a constant pressure process, like we would see through a heat exchanger, a condenser, or evaporator, also is a constant temperature process if we're inside the liquid vapor region. Now, one of the important characteristics of a Carnot cycle is that it achieves its heat transfer with the surroundings during constant temperature processes. Well, if we have a substance that is changing phase while that's happening, then it's also a constant pressure process. So this is something that is achievable in normal engineering equipment like heat exchangers. So that's the nice thing about having the substance change phase. So if we take our Carnot cycle and place it fully inside the liquid vapor region to begin, then these two processes here, this is constant pressure, but it's also constant temperature. So that's our constant temperature heat rejection process. This is our constant temperature heat addition process. And then the two reversible adiabatics are this process and this process. So just to use the same numbering as we did on the previous slide, we have a reversible adiabatic compression, a constant temperature heat removal, a reversible adiabatic expansion, and a constant temperature heat addition. So again, the Carnot cycle is just a rectangle on TS coordinates, but here it's placed inside the liquid vapor region. So these two processes are also constant pressure. Now, I happen to have started this at the saturated vapor line and ended it at the saturated liquid line, but there's nothing particularly special about that. And we'll see we need to move some of these points anyway to get a practical cycle. So currently, this is a Carnot cycle operating in the liquid vapor region. So each of these four processes would require a component or a piece of equipment in order to achieve it. So one possibility for this cycle is as follows. We start with a compressor, and that would have to be a reversible adiabatic compressor, then a condenser for our constant temperature heat removal, and then a reversible adiabatic turbine to drop straight down on the TS diagram, and then finally a constant temperature heat addition, which would take place in the evaporator. So this is a possibility for achieving a Carnot cycle inside the liquid vapor region as a refrigeration cycle. Now there is problems with this. The first problem is with this compressor. What we're trying to do here is take something that is a liquid vapor mixture here and compress it until it's a saturated vapor here. We'll just go back and review our TS diagram. So we're talking here about this process. A mixture compressed to become a saturated vapor. So it's very difficult to compress a liquid vapor mixture. There is certainly equipment that is good at compressing vapors, and there is equipment that is good at compressing liquids, but to do both of them at the same time is a very, very difficult challenge. In fact, such equipment really doesn't exist. And here we're asking it to happen isentropically, or absolutely no irreversibilities. Well, that's essentially impossible. So instead of compressing this liquid vapor mixture, we need to make a change to this system. So what we're going to do is propose a different compression process. And the way that this is going to happen is we're going to leave that liquid vapor mixture in the evaporator longer, so a larger evaporator, so that point 1 is actually on the saturated vapor line. It may in practice be a little bit outside, but for now we're going to stop on the saturated vapor line. So point 1 used to be here, but we're completely evaporating all of the liquid until we get to the saturated vapor line. Now this flows into the compressor, and a reversible adiabatic compressor would again be a vertical line, so we would go straight up, but now notice the entire compression process is in the vapor region. Now that's going to continue upwards until it reaches the condenser pressure. So this line is a line of constant pressure at the condenser pressure. So notice this has to go to quite a bit higher temperature in order to get to that condenser pressure. So this point here is at a higher temperature than that point. So the condenser now, this is the inlet to the condenser. The beginning portion of the condenser, there's no condensation happening at all. Instead, that superheated vapor is being cooled down until at this point it finally starts to condense, and then the condensation happens until it becomes completely saturated liquid at this point. So you'll notice that we're no longer talking about a Carnot cycle here. This still has the characteristics of a Carnot cycle. So does this, constant temperature heat addition. This still has what is required for a Carnot cycle, a reversible adiabatic compression. However, this is no longer a constant temperature heat removal process, so we no longer have a Carnot cycle. This is now called a vapor compression refrigeration system, and it's vapor compression because the compression is being achieved completely out in the vapor region, where we can do so much more efficiently. Now it turns out there's still another problem with this cycle, and that is the turbine. So here we're asking a turbine to do something that we had difficulty asking a compressor to do over here. Notice we're feeding this turbine a saturated liquid, and immediately as that expansion starts to occur, there's going to be vapor forming in there until at the exit we have a liquid vapor mixture. Well, those are very difficult conditions for a turbine to operate under, and it's impossible to create an efficient turbine that does that. Not only that, but if we were to look at the amount of energy that we could recover in that turbine, it would actually be very, very small. So it's certainly not worth the added complexity of a turbine in this case. So what we do to solve this problem is we expand through a throttling valve instead. So the turbine in our initial look, or in our initial schematic, is replaced with just a simple throttling valve. Now, through a throttling valve, there is an increase in entropy. So rather than this being a vertical line, it now drifts off to the right as we go through the throttling valve. So this is the throttling process, an increase in entropy as we drop from the high pressure to the low pressure. So now we have our final vapor compression refrigeration system. These three components have not changed. The only difference is our compressor is now operating out completely in the vapor region, and the turbine is replaced with a simple throttling valve. Now the next thing we want to look at is the isentropic efficiency of the compressor. So far we've looked at a compressor that is isentropic, meaning a vertical line on the TS diagram. Well, a real compressor is going to drift off to the right as the compression progresses, so that we'll actually hit the condenser pressure up here at a higher temperature. So this is what a real compression process would look like, and this original one was the isentropic process. So the exit temperature of the real compressor will be higher than the isentropic compressor. And we're going to talk about the isentropic efficiency of compressors in the context of refrigeration systems a little bit later as well. Now, so far we've been talking about this vapor compression refrigeration system in the context of a TS diagram. And the reason we did that is because we started off with a Carnot cycle, and a Carnot cycle is very easy to draw on TS coordinates. Well, it turns out that a TS diagram is not commonly used in the refrigeration industry. Instead, these refrigeration cycles are normally plotted and studied on a pH diagram. So this is the first time that we've seen a pH diagram, so we want to orient ourselves to what things look like here. So what we're showing so far here is the saturated liquid and the saturated vapor lines, and the critical point is up top. So the thing that's different about this is the saturated vapor line actually doubles back on itself. So most of the line has a positive slope, the same as the saturated liquid line. So that's something that's a little bit different about a pH diagram. We're going to see an actual pH diagram here in a few moments. This is just a simplified sketch so far. Next thing we want to know is, what does a line of constant temperature look like on pH coordinates? Well, out here in the liquid region, it's essentially a vertical line, same as it was on a PV diagram. In the mixture region, it's a horizontal line, again the same as it was on a PV diagram. But out in the vapor region here, our line of constant temperature curves downwards like this. And if we look at different temperatures, those curves are all going to be similar, but of course they slice through the liquid vapor region at different pressures. So this is looking at decreasing temperature as we go in that direction. Another thing we want to know about a pH diagram is what does a line of constant entropy look like. Now we're really only interested in those lines out here in the vapor region because that's where the compressor is operating, and the lines of constant entropy are a very handy reference to looking at how close to isentropic our compressor is. Well, lines of constant entropy are curved upwards like this. So that is actually showing a bunch of lines of constant entropy, and the entropy is actually increasing in that direction. So this is a look at a real pH diagram. And so the vertical axis here is pressure, horizontal axis is enthalpy. We see our saturated liquid line there, critical point at the top, saturated vapor line coming down here. Now, rather than cluttering up this liquid vapor region with a whole bunch of lines of constant temperature going through it, what's typically done is there is just tick marks on the saturated liquid and saturated vapor lines that indicate the temperature, and then we can just connect those with a straight line at whatever temperature we're interested in. In the vapor region out here, these are the lines of constant temperature tailing downwards like this. These steeper lines heading up like that are lines of constant entropy. So those are the most important lines, but this one also has lines of constant specific volume angling up this way. We don't really use those in this course, however. So that's just a look at a pH diagram actually drawn to scale. Now, going back to our simplified pH diagram, the next thing we want to do is show our cycle on these coordinates. So the first process is our isentropic compressor. So this is the inlet to the compressor, and that's the exit, and I'm showing the isentropic one here, so I've labeled the endpoint 2s. So this is along a line of constant entropy out in the vapor region. If we look at a real compressor, it is going to drift to higher and higher values of entropy as the progression goes on. So that means it's going to drift to the right. And notice it's going up to the same value of pressure because we need the exit of both the isentropic and the real compressor to be up at the condenser pressure. The next process is the condenser, and because that's a constant pressure process, it's just a horizontal line on the pH diagram. So this is our condenser going from the exit of the compressor straight over to the saturated liquid line. The throttling valve is a line of constant enthalpy. That's one of the reasons why choosing H is such a convenient choice for the horizontal coordinate, is our throttling process is then just a vertical line. Finally, we get to the evaporator, which is another line of constant pressure, so another horizontal line from 4 back to the inlet of our compressor. So a pH diagram is a very useful and very convenient set of coordinates for refrigeration systems because 2 of the lines are just horizontal lines, one of them is vertical line, and it's only the compression process that is a little bit more complicated out here in the vapor region. Now, there's lots of other reasons, other than it being easy to draw, why it's nice to have enthalpy as this horizontal coordinate, and we're going to show some of those reasons now. So this is the same diagram, just shrunk a little bit so we can write underneath it. What we want to look at is this process from 4 to 1. So if we drop straight down from point 1, that'll be our enthalpy at 1. And if we drop straight down from point 4, that will be our enthalpy at point 4. And if we had this drawn to scale on a good pH diagram, we could read those two numbers right off of the diagram. Well, the heat added in the evaporator is QC because that's the heat coming from the cold reservoir, and that's going to be equal to H1 minus H4. This is just coming from our energy equation. Now if we look at that on a rate basis, then Q dot C is going to be equal to M dot times H1 minus H4. So this is a quantity of primary interest in refrigeration systems. That's the rate at which this refrigeration system is drawing heat out of the cold reservoir. That's the reason we went and bought this refrigeration system, was to do that for us. So this is called the refrigeration effect or the refrigeration capacity. Both of those are essentially interchangeable terms. And of course, as long as we know the mass flow rate through our refrigeration system, we can tell the refrigeration capacity just by the horizontal separation between these 2 points on our pH diagram. The longer that line is, the larger our refrigeration capacity. The next thing that we can learn from the pH diagram is about the work required by the compressor. So again, energy equation applied to the compressor, we get WC equals H1 minus H2 on a per unit mass basis. But if we multiply both sides by the mass flow rate, we get the power requirements of our compressor as m dot times H1 minus H2. So again, it's the horizontal distance between these 2 points on our pH diagram that relates directly to the power required by the refrigeration system. If we're interested in the isentropic efficiency of this compressor, we can tell that by looking at the pH diagram as well. Because notice H1 minus H2 is the actual power, so that's the denominator of our isentropic efficiency, and H1 minus H2S is the ideal power. Well, that we can get right off the pH diagram from dropping down from this point and getting a third value of the enthalpy. So notice the efficiency of the compressor you can actually estimate just from the relative length of this line and this line, or the horizontal separation between those points. So this distance divided by that distance is the efficiency of the compressor. So I would say here that's about 80%. And you can actually figure out this efficiency without ever reading off H's. If this is drawn to scale, you can literally just measure this with a ruler. That's an inch, that's an inch and a quarter, divide the two numbers and you get your isentropic efficiency. You don't actually ever have to work with enthalpies if you don't want to when you're reading these off of a diagram that is drawn to scale, of course. Another thing that we can do directly off the pH diagram is see the coefficient of performance, because coefficient of performance is QC over WC. Well, that's H1 minus H4 divided by H2 minus H1. So let's look at our pH diagram and see where those come from. So there's these 3 values of enthalpy that we can read by dropping straight down. This is our compressor work, that's the denominator, H1 minus H2, and this is our refrigeration effect. So the ratio of this line divided by this line is the coefficient of performance. So here you can see the coefficient of performance of this particular system is very close to 1, maybe a little bit bigger than 1. That might be slightly larger than this, but you can really tell at a glance whether this is a high coefficient of performance or a low coefficient of performance. This happens to be quite a low value, but again, this is just a sketch. It's not drawn to scale from any real data. Next thing I want to look at is the 2 temperatures that this system is operating between. So this is just a repeat of our pH diagram. We know that is TH and this is TC. Now everything that's being plotted here is the properties of the refrigerant or the working fluid as it goes around this cycle. So we're plotting properties of that substance on pH coordinates. So this means that inside of the evaporator, for instance, the temperature of the refrigerant is Tc. Well, we need to realize that we need to get heat to flow into the refrigerant inside of the evaporator. So the direction of heat flow needs to be from the surroundings into the system as we go through the evaporator. So that means that the cold region that we're cooling has to have a higher temperature than Tc. Or another way to put that, the temperature of our refrigerant, Tc, has to be lower than the temperature of the region that we're trying to cool. So if this is a household refrigerator, we want this cold region to be probably about 4 degrees C, which is a typical temperature inside of your refrigerator. So that means the refrigerant inside the evaporator has to be something less than 4 degrees C. And typically it's quite a bit less than 4 degrees C. It would be minus 20 degrees or so, because we need this temperature difference to drive the heat flow. So the heat has to flow from the surroundings into the refrigerant, so the temperature in the surroundings has to be higher than the refrigerant. Now we want to think about the same thing happening in the condenser up here. This is the temperature of our refrigerant, but in the condenser we want the heat to flow out of the refrigerant into the surroundings. So our surroundings are going to have to be cooler than our refrigerant in the condenser. So if this is the kitchen at 20 degrees C, the temperature of the refrigerant inside of the condenser needs to be hotter than that. If it's colder than that, heat's not going to flow in the right direction. So in order to get the heat to flow from the refrigerant into the surroundings, the refrigerant needs to be hotter than the surroundings. So we end up having to have our refrigerant colder than the cold region that we're trying to cool and hotter than the warm region in order to get these temperature differences so that heat will flow in the right direction. So if we go and buy a refrigerator to cool off this space and reject heat to this temperature, we need to realize that it's actually going to have to operate between a wider temperature range than that in order to get enough heat transfer to do its job. So a refrigerator is always working harder than it would have to if these temperature differences weren't required. So if we didn't need these temperature differences here to drive heat transfer, then we could have our refrigerator working between these temperature limits. But because we need those temperature differences to drive the heat transfer, our refrigerator has to actually work between a wider range of temperatures. Therefore, it needs to work harder. Now I want to define a term here that is often used, very often used, as a unit for refrigeration capacity or refrigeration effect. Now, perfectly acceptable units for that are watts or kilowatts or perhaps BTUs per minute or BTUs per hour. Those are all a rate of energy transfer or a rate of heat transfer, and we've used pretty well all of those so far in the class. Well, in the refrigeration industry, there's another unit that is used for refrigeration capacity, and that is a ton of refrigeration. And the conversion between a ton of refrigeration and these other system of units is as follows. So 1 ton of refrigeration is 200 BTUs per minute, or 211 kilojoules per minute if we want to use an SI unit. So that's how a ton of refrigeration is defined. Now it's kind of a funny unit. You don't think of a ton as being a heat transfer rate, but that's what it is. Now the way that it got that name is if you happen to have a refrigeration system that has a capacity of 1 ton, then that is exactly what you need to freeze 1 ton of water in 24 hours. So if you're in the ice making business and you want to make a ton of ice every day, then you need a refrigeration system that has a capacity of 1 ton. That's where that name comes from. The last thing we want to talk about is what is meant by an ideal vapor compression refrigeration system. Well, an ideal vapor compression refrigeration system is simply one where the compressor has a 100% isentropic efficiency. That's what the word ideal tagged onto the front of vapor compression refrigeration system means. The compressor is 100% efficient. It does not mean that the coefficient of performance is at its maximum value. In order to achieve the maximum coefficient of performance, we need more than just having a 100% efficient compressor. We would also need to go back to our Carnot cycle. And as we realized, it's not practically possible to implement a Carnot cycle. So when you see the word ideal, notice it does not mean we're operating at the maximum possible coefficient of performance. What it does mean is that the compressor has 100% isentropic efficiency.